Okay, so in this video we are going to look at how to calculate the edge betweenness for each of the edges in a graph. So let us say this is a given graph. So the procedure is like this. So we first run the breadth first search algorithm starting from each vertex, which means we'll run breadth first search starting from A and then breadth first search starting from B and C, D, E, F. So each of the vertices. So the breadth first search procedure is something like this. You start with, say, here from A. So A is said to be at level 0, and from A we can reach B and E with one hop. So there's B and E are said to be at level 1. From B we can reach F and G. So these two are at level 2, and we highlight those edges which we call as a tree edge. That are used to reach a vertex for the first time on the shortest path. Now from F we can reach D at level 3, which is one more than the level of F. So these are the node levels for the vertices on the breadth first search tree starting from A. So now what we do is we try to find the number of shortest paths from A to every other vertex. So for that we again use the level numbers. So the number of shortest paths from A to itself is 1. That's our initial condition. Now for any other vertex we find the number of predecessor vertices at the earlier level and we add all those shortest path numbers. So for example, for B, which is at level 1, the number of vertices or the vertices that are at level 0, 1 less than the level 1, which is level 0, is A. So in this case, what will be the shortest path from A to A? That is also the number of shortest paths from A to B, which is 1. Same case for E. At level 1, the vertices at level 0 is just A. So what will be the number of shortest paths from A to A? That is also the number of shortest paths from A to E. Now in the case of F, which is at level 2, there are two vertices at level 1, which is B and E. So the number of shortest paths from A to F is the number of shortest paths from A to B plus the number of shortest paths from A to E. So that will be like this 1 plus this 1, which is 2. The case of G, which is at level 2, the predecessors at level 1 are just B. So the number of shortest paths from A to B is the same as the number of shortest paths from A to G because we have to go through that predecessor B. Now in the case of D, which is at level 3, the predecessors are F and G at level 2. So the number of shortest paths from A to D will be the number of shortest paths from A to G, which is 1, and the number of shortest paths from A to F, which is 2. So 1 plus 2 is 3. So basically you have one shortest path from A to G and two shortest paths from A to F, which are in this case ABF and AEF. So to get to D from A on the shortest paths, we can make use of any of those shortest paths to the predecessors. So in the case of D, G has one shortest path to A, F has two shortest paths to A. So you can reach D through 1 plus 2, which is 3 shortest paths from A. So that's what it means, to find the number of shortest paths from A to every other vertex. So once we have this for the BFS tree rooted at A, we will go ahead and calculate what is the flow that is possible on each of those edges on this BFS tree rooted at A. So for that, we distribute a unit of one unit of flow at each of the vertices other than the root, which is A. So we start from the vertex which is at the bottommost level, which is in this case 3, and the vertex is D. So for vertex D, we will split that one unit of flow proportionally to its predecessors. Now the predecessor for D or predecessors for D are F and G. So G has one shortest path from A and F has two shortest paths from A. So we divide that one unit of flow proportionally, so 1/3, because D has three shortest paths from A and two of them come from F and one from G. So we divide that one unit of flow like this: 1/3 goes to G and 2/3, because two of the shortest paths come from F, we divide 2/3 of that 1 unit of flow, which is 2/3 is 0.67, so goes to F. So G gets 0.33 units of flow. It combines that with its own 1 unit of flow, so that's 1 plus 0.33 is 1.33, and G has only one predecessor, which is B. So it just sends that 1.33 to B. On the other hand, F combines that 0.67 that it gets from D with its own 1 unit of flow, which is 1.67, and F divides that flow proportionally to two of its predecessors, because F has two predecessors, B and E, and from each of them it gets 1 unit of flow. So it divides that 1.67 by 2. So 1.67 divided by 2 is 0.835. It sends that 0.835 unit of flow to B and another 0.835 units of flow to E. So B gets that 0.835 from F and 1.33 from G. So it adds them, which is like 2.165, and it adds its own 1 unit of flow, which is 3.165, and it sends to its predecessor, which is A. So similarly, E combines that 0.835 units that it gets from F. There are no other descendants of E, so F is the only descendant, so it gets that 0.835 plus its own 1 unit of flow, and it combines with that, and it sends 1.835 units of flow to A. So A gets 3.165 units of flow from B and 1.835 units of flow from E. So that is the kind of flow on this BFS tree rooted at A. So we repeat that on the BFS trees rooted at each of the vertices. So this is a BFS tree rooted at B. So it starts from B at level 0. A, F and G are the descendants at level 1. And from A to E we can there's a tree edge, and E is at level 2, one more than level of A. Similarly, D is at level 2, one more than the level of F, because F is kind of alphabetically smaller than G. We can make F as the edge, FD as a tree edge. So it doesn't really matter to highlight the edges, but I just want to maintain the consistency that we earlier used for breadth first search. So now what we do is, once we have the node level numbers, we again find the number of shortest paths from the root of the BFS tree, which is B, to each of the vertices. So from B to itself is one shortest path. From B to A is again one shortest path, because A is at level 0 and the vertices at level A is at level 1 and the vertices at level 0, or this one vertex, which is B. So from B to B is one shortest path, so B to A is also one shortest path. F is at level 1 and its predecessor at level 0 is B, so there's one shortest path from B to F and one shortest path from B to G. Now E is at level 2, so it has two predecessors, A and F, at level 1. There's one shortest path from B to A and one shortest path from B to F, so it is 1 plus 1, 2 shortest paths from B to E. Similarly, D is at level 2. It has two predecessors, F and G, at level 1. So F has one shortest path from B, G has one shortest path from B, so 1 plus 1, 2 shortest paths from B to D. So now we'll have to find the flow on each of those edges rooted at on the BFS tree rooted at B. So now there are two vertices, D and E, at the bottommost level, which is level 2. So again, initially we distribute 1 unit of flow to all the vertices other than B, and so this the vertices at the bottommost level can do it independently. Likewise, vertices at a particular level can also aggregate the flow from the descendants and send independently. So D divides its 1 unit of flow proportionally to F and G. So it has one shortest path from F and one shortest path from G. So 1 divided by 2 is 0.5. It sends that 0.5 units of flow to F and another 0.5 units of flow to G. Similarly, E divides its 1 unit of flow proportionally to two of its predecessors, A and F, equally, because both give one shortest path to E. So 1 divided by 2, 0.5 units of flow go to A and another 0.5 units of flow go to F. So F gets 0.5 from D and another 0.5 from E. It combines them, which is 1, and adds its own 1 unit of flow and sends the 2 units of flow to its predecessor, which is B. So B gets 2 units of flow from F. On the other hand, A gets 0.5 units of flow from E, which is the only descendant for A. So it combines that with its own 1 unit of flow, so it is 1.5, and sends that 1.5 units of flow to B. Similarly, G combines its 0.5 units of flow from D, which is the only descendant for G, and sends that 1.5 to B. So B gets 1.5 from A, 2 from F, and 1.5 from G. So we repeat this process on the BFS tree rooted at each of the vertices. So G, then E, then F, and D. So we put together the flow information that we have on the BFS trees rooted at each edge, on each vertex like this. So now we sum up the flow that we have calculated for each of the edges. So for the edge AB, we need to add up the numbers we have on each of these BFS trees. So for AB, it is 3.165 here, and AB is 1.33 here. So 3.165 plus 1.33 plus another 1.5 here, and on this we have 0.5 plus 0.835 plus another 0.67. So if we add up all these things, we get 8. So since the edges are undirected, which means bidirectional, the flow can be on both directions, we divide this total by 2. So 8 divided by 2, which is 4, is the edge betweenness for the edge AB. Similarly, for the edge, say for example BF, we add the numbers 0.835, another 0.835, plus here we have 2.0, plus we have here another 2.0, plus we have 0.835, plus like 0.835. So if we add up all the numbers, we get 7.34, divide again by 2. That will be the betweenness of this edge BF. So we repeat this process like this for each edge, add up the flow that we have calculated for that edge in each of those BFS trees, add up that number and divide the sum by 2. So that will be the betweenness of the edges that we have for that graph, and that will be same as what we have in this graph that we earlier used for motivation. So this is the graph we just went through, and I just replaced the alphabets with numbers here, and so these are the edge betweenness values of the edges. So with this we stop.